Going to continue talking in Unit 2.5, the periodic table. Going to look at maybe a little bit of the more trends that we're going to see. And again, as always, having a periodic table handy, always going to be super important. Always going to be an important thing to have when talking about some of these trends and or the periodic table. So one of the first things that we're going to look at today, in my mind, is probably the most important trend on the periodic table. Because I think for the most part, it is one of the more intuitive trends on the periodic table, and that a lot of the other trends piggyback off of this trend. And that is the atomic radius. How does the atomic radius and what is that even measuring? It's actually measuring the distance between the nucleus of the nucleus. So from nucleus to nucleus of an atom. And we show the 7 diatomic molecules, and those are going to be some elements that you're going to need to eventually at some point in time know. And these are the 7 diatomics that we are measured their radius. So it's from one radii to the other. It kind of shows. Now, if we can see we have that 30 picometers. That's very small because you're using pico. So that's somewhere on the order of times 10 to the -9th, I believe. And so they're small. It's really small. But they do get bigger as they get, kind of as you can see, that some of the bigger elements. And there is a nice trend for this, and we will kind of look at that trend as we go further with it. So here's kind of a just looking at the trend of the atomic radius. It's not a periodic table, it's just the main group elements, and that's when we look at a lot of these trends, we're only going to worry about the main group elements. And so as we go down the periodic table, we can see that the atomic radius is getting bigger. Well, I think that makes a lot of sense, very conceptual sense. If you look at your periodic table and you go from hydrogen to lithium to sodium to potassium to rubidium to cesium to francium, the atomic number is getting bigger. Not only that, if you remember drawing your Bohr models, hydrogen only has 1 circle. Well, lithium has 2 circles. To draw that, you have to usually draw them bigger and bigger and bigger as you go down the periodic table. Because as you go down the periodic table, the atomic radius gets bigger. As we can see that. Because the number of circles gets bigger with it. And so that's, for me, I think that's very intuitive. I'm hoping that drawing the Bohr models, and a lot of people probably didn't want to draw the Bohr model of, say, lead, because it was so big, because it required 6 circles. Well, the same thing would be said for, say, cesium. It would require 6 circles. And as you go down, the number of circles is going to increase. The size, the physical size of your Bohr diagram will also get bigger. Now, the one that's maybe a little bit less intuitive is going from left to right. That requires a little bit of understanding of what's going on as we go from left to right. We see that the atomic size decreases. Okay, that's one thing, but why is it decreasing? Well, if we think again to our Bohr models, lithium and beryllium have a very similar Bohr model. They're both going to have two circles. Both of them are going to have two electrons in that first circle. They are going to differ in the number of electrons in that outer circle. Well, the other thing that's going to happen is that beryllium is going to have more protons in the nucleus. And protons have what charge again? Because the protons have a positive charge and the electrons have a negative charge, we can see that remember, according to physics, opposites attract. So therefore, that proton in the middle is going to attract the electrons that are hanging out outside. And therefore, we're going to pull them into the middle just a little bit more. And then when you jump all the way over to, like, say, boron and carbon, you're not increasing the number of circles by going over to boron and carbon. The only thing you're increasing is the number of electrons and protons. But because, again, those protons have a positive charge, they're going to pull those electrons in because they have the negative charge. They're going to pull them in, just keep pulling them in, and it's going to pull those outer rings closer and closer and closer to the nucleus. Well, they're able to go there because the positive charge in the middle is able to kind of get closer or attract those out that first ring just a little bit more. Because if you look as we go down, say like nitrogen to phosphorus, the atomic radius still gets bigger. Okay? But as we go from, say, phosphorus to sulfur, the atomic radius is going to decrease. The smallest elements on the periodic table are going to be the noble gases. They have that full shell. Okay? Now, why all of a sudden do we see neon being small and then sodium being like way bigger? All of a sudden, you have another ring, another energy level for those electrons to spread back out. Yes, you have more protons, but it's that third energy level that's going to kind of bump everything back out and kind of allow for that space to happen. And then they start pulling themselves back in as they go from left to right, all the way over to argon. And then the same thing happens when it bubbles back out to potassium, and then starts pulling everything back in all the way over to krypton. So that is what's happening, or at least that's the way I have found to think about as why is this happening as we kind of go through that. And so I think that helps us kind of figure out, okay, how is this going? And again, if you're going to memorize one of them, memorize atomic radius and understand why the things happen the way they do, I think can be very beneficial. Because the rest of the trends are pretty much opposite of atomic radius. So let's think about it. The correct order of increasing atomic radius, smallest to largest. So, first thing to do maybe would be to find which one is the biggest one altogether. Well, that would be the one that is the farthest one down, which would be these two with rubidium. Okay. The one thing that we're allowed to kind of then verify then is that potassium is also there, so potassium would also be the next largest one. Now, what we have to then look at and think about, which one of these is going to be bigger? Because that's going to be the difference. If magnesium is going to be bigger than sodium, A would be the answer. If magnesium is smaller than sodium, then B would be the answer. Based on their locations and the fact that it gets smaller when you go from left to right, the smallest element is going to be magnesium in this group. So, ionic size depends upon the number of electrons, very important, and kind of where they lie at. So, the atomic radius, the normal atomic radius, is the yellow that we can kind of see here. What happens is the ions are going to change the atomic radius as well. Now, as you look at this, the trend is still there that as you go from left to right, the atomic radius decreases for the normal size atoms. Well, if a smaller atom loses electrons, it is also going to get even smaller than its parent as well. Now, why all of a sudden does oxygen and fluorine, why do they get bigger? Well, they're gaining electrons, meaning you have more negative in those rings than you had before. Opposites might attract, but like charges repel. To allow for those electrons to repel each other, they have to get bigger. And so the atomic radius gets bigger. The numbers that we can see here are the actual atomic radius for those elements. Those are tabulated values. They can be found in your text and or other reference material. As we look at the general for the neutral atom, it gets smaller as we go from left to right. And when you start losing atoms, the same thing happens. Now, when you're gaining atoms, the same trend happens, that oxygen is bigger than fluorine. As we go down, the atomic radius also gets bigger for the ions, whether they lose electrons or if they gain electrons. So ions tend to be just a little bit trickier because you have to identify what is happening. Is the atom gaining or losing electrons? If it's losing, it's going to be smaller because that positive charge in the middle is going to screech in and go from there. Whereas when they're negative, gaining electrons, they balloon up to allow for that space to happen. So based on that information, let's think about that. The statements below, which one is false? Which one is? Ionization energy is the energy required to remove an electron. That's because they don't just randomly just willy-nilly fall off. You're like, oops, I lost one. That doesn't happen. You need to pull one away. Now, ionization energy is a trend on the periodic table. It is opposite of that of atomic radius. So if the atomic radius gets bigger, that means the ionization energy is going to get smaller. Meaning a small ionization energy means that it's going to be easy to pull an electron away. I look at this as kind of an idea, an analogy, if you will, that if you had a group of students in the gym and you have, say, a couple teachers standing at center court. Well, there's a circle around the center of the court. And if you have just one or two students standing on that line, it's probably, chances are, those students aren't going to be able to get away with any ease. They wouldn't be able to leave the gym with any ease or without the teachers that are in the center of the gym at center court without knowing that they're leaving. Now, as you add more and more students or more and more electrons, you have to expand the number of circles that are there. As you expand these circles and the students are farther and farther away from the nucleus or the teachers, it is going to be easier for those students or the electrons on the outside to go away and not get caught, so to speak. Well, it's the same thing with the electrons. It's those ones that are on the outside, the farthest ones away from the nucleus, will just find themselves being pulled away with less energy required. So as the atomic radius gets bigger, it is easier, requires less energy to pull an electron away. As the electrons get closer to the nucleus, the atomic radius decreases. It makes it harder to pull an electron away, meaning it requires more energy. Think about it this way. If you only have two $1 bills and somebody wants to take your dollar bills away, and this is the only $2 that you have, you're not going to be, oh, here you go, as easy. It's going to take a lot of energy to pull those $2 away, or even just $1 at a time. If I were able to get $1 away, getting that second dollar is going to be even harder. So as you lose electrons, it becomes more and more difficult to lose more electrons, meaning it takes more energy to do that. Now, there are some exceptions, as there always are in chemistry. We're not too worried about these exceptions when it comes to my class, for the most part, because we want the basic big trend. Okay? There are those anomalies. There will be some exceptions that we will really worry about, and then sometimes that we won't. We can see here, why are they getting so much astronomically bigger from just losing a second electron? Well, that's because that second electron is that noble gas configuration, that octet. So to lose anything more than that, it really takes a lot of energy for that to happen. And so that's why those elements don't like it. That's why they hold on to them. So here's a graphical representation of that same information. It's just as we go down the periodic table, ionization energy gets smaller. As you go from left to right, the ionization energy increases, which is exactly, again, completely opposite of the atomic radius. And again, the kind of the conceptual understanding of the why is that it's easier to pull electrons from large atoms. It's hard to pull electrons from small atoms. So that's where we get some of these trends that we see here. Now, electronegativity is the ability for an atom to gain electrons. Meaning, hey, I want an electron, bring one on over to me. Now, this again is going to be opposite from the other, from the atomic radius, in that as you go down the periodic table, they have a less ability to gain electrons. Those protons in the center of the atom can't be like, hey, over here, I need some electrons. I got a bunch of positive charge here. That doesn't happen, because they're so big, they can be kind of shielded in a way. The closer, when the atomic radius decreases, the ability of those electrons to be attracted in increases. So then the protons can wave and say, hi, I'm over here, look at me, I got a bunch of positive charge, come over to my atom, and so that happens. Now, when it comes to ionization energy and electronegativity, we're dealing with the main group elements. That would be groups 1, 2, 13 through 18. And in all reality, electronegativity doesn't have any bearing on group 18 because they have their octet. They're not really going to add any to them. So many reference materials are going to say we don't have electronegativity values for the group 18, the noble gases, which they are correct, but when we rank them, they would have extremely they're very less likely to have that with that going with there. So that's again based on that atomic radius, using that to determine which one's kind of why is this going to happen. Large atoms aren't going to be able to attract those electrons to their atom because they're shielded. All the other things are in the way. You can't see it. Okay? In a small atom, the nucleus is more visible to other electrons, and because of that, they're able to be seen. Here's a chart of electronegativity values. Again, tabulated. Don't need to write this all down because that would be a lot of information. When we look at this, we can see that fluorine has the highest electronegativity value of 4. As we go down, the atomic radius gets bigger, the electronegativity value goes down. So if atomic radius goes up, electronegativity value goes down. As we go from left to right on the periodic table, the atomic radius gets smaller. Because it's getting smaller, the electronegativity value goes up. So they're opposites again. They're opposites. And even with those metals, which are very rarely going to ever attract an electron, because their atomic radius is so much bigger, they're less likely. They're going to lose them before they gain them. And because they're really big, say like cesium, it doesn't take much for them to lose them. And it's very hard for them to even gain them because they're so large. There's such a shielding effect. And that brings us back into another trend that we're going to talk about tomorrow, and that is which ones lose, which ones gain. We already should probably know that, but we'll talk about more of that tomorrow.